So today's paper is called Gemini Fast Failure Recovery in Distributed Training with In-Memory Checkpoints. And so let me just, yeah. So this paper is about how to recover from crash failures, but in a distributed training system, as Alexi mentioned, it's kind of different from what we have seen in database systems because the guarantees that you need here are different. So why would you need something like this? To give a brief background, AI models have been getting larger and larger. So in the past couple of years, they have been trained on lots of GPUs because we have more training parameters and you cannot do it on a single machine. So when you add a lot of machines, what happens is that the rate of failures also grows. So we have to deal with it in some way. And I didn't know how much of an AI background you have, so I just wanted to give a brief background about how people do distributed training. So mainly there are three main approaches. One is called model parallelism, which means that let's say you have an AI model, let's say this is a neural network, and you split the model itself. So on the left side, you can see that you have different layers on different machines. So you have to go through all the machines to be able to train your model. Another way of doing it is data parallelism, which means that you have the same model, but you split your data and feed each machine with a different subset of the data that you have. And you can also do a hybrid approach where you both split the model and also the data at the same time. The use cases are different. For example, if your model doesn't fit a single machine, you might need to even split the model, or even like in scenarios where you cannot fit your data into a single machine, you would need to do things like this. And also you will get parallelism because you can use lots of machines at the same time. And another quick background is that people do two different ways, mainly two different ways of distributed training. One is called synchronous, which this paper talks about that. And the other one is asynchronous. In the synchronous approach, you don't need to care about the different kinds of synchronous, but the main idea is that so AI training is done in batches. Like you do it in iterations, and then so if you have lots of machines, they have to coordinate in the synchronous approach to get all those updated weights. So you learn something and you have to let all the machines to know about what you have learned so far, and then continue training your model again. So what you can see here is that in the synchronous approach, all the machines, even if a machine takes a long time, you have to wait for that machine because all the machines should get the updates and continue. But what you see in the asynchronous approach is that one machine can continue without waiting for the other ones. So here you can see it's more messy. Like one machine goes further, goes into the next iterations. So the trade-off here is that the synchronous approach might be slower because you have to wait for the stallers, the machines that are slower than all the other machines, but you get better model quality because you always get all those updated values for your model and then continue on top of that. But in the asynchronous approach, you can go faster, but you might not get the best accuracy. So with all the things being said, the main problem is that with large model, we have many GPUs, and like what we have seen in distributed systems, you get a higher probability of failures because now you have lots of machines, and even if one machine has a very low probability of failing in a cluster of I don't know how many thousand GPUs. Um, it's, I mean, you see GPU failures much faster. So the paper comes up with an example, with a real world example, that in training OPC 175 billion, there were 178,000 GPU hours wasted because when a GPU fails, and the paper talks about the synchronous approach, you have to wait for uh, another GPU to get that task, and then you update all the values. So what people use is called checkpointing. Checkpointing is just getting a snapshot of the model state at this moment, and then store it somewhere so that if a machine fails, you can just go get the latest checkpoint and continue from there. This is the main approach that people have been using to recover from failures in distributed training. But there are two main things that are important. Checkpoint frequency, because you want to checkpoint as fast as you can, because if you don't do it, let's say I checkpoint every 12 hours. If I fail at the 10 hours point, I have to get the model state that was captured 10 hours ago. So you will miss lots of work that has been done. And also checkpoint retrieval time is important, because if you have to wait for a long time to get the checkpoint from wherever you store it, we talk about that, you will waste some time because you cannot continue and make progress. And also to give an overview about checkpointing, this is how you can imagine it. So these are the iterations that the model is being trained, and you checkpoints. So you take checkpoints, and then when a failure happens, so here a failure happened when checkpoint 3 was being processed, you have to get the latest checkpoint before that, which is checkpoint 2, and continue from there. So this part is the wasted time, because you have to redo some work and also wait for getting the previous checkpoint from where you stored it. And the paper mentions that existing solutions, what they do is that they store checkpoints in remote persistent storage, which causes some problems because you cannot increase your checkpoint frequency, because it takes a long time to just store the checkpoint in remote storage. And also retrieval time is slow because you have to go read it from the disk. So Gemini proposes a new solution. It says, why should we go and store everything in the storage? I mean, in the persistent storage. Let's just have a storage hierarchy, which starts at my own CPU memory. So a GPU is training a model. It also has lots of memory. I mean, if you see these GPUs, they almost have the same amount or even more amount of CPU memory than GPU memory. So you can utilize that to store the latest checkpoint. And also, if that's not enough, you can use another machine's memory, or in the worst case, roll back to using the remote storage. So Gemini's main idea is doing something like this so that you can capture those checkpoints faster, and also the retrieval time is much better. But there are two main challenges to do this. One is that how do we maximize the probability of recovering from checkpoints? So what I mean is that it's like a caching problem, because you would like to have your checkpoints as close as possible to you. So how would you place the checkpoints so that you rarely go to the persistent storage? And also the second challenge is how to minimize the interference of checkpoint traffic with model training, because CPU memory and GPU memory have to send information for training. And now we are adding another thing, which is taking checkpoints. So we don't like to get these interfering with each other, because it will slow our training process. So for the first challenge, Gemini has two approaches. One is group placement. So in group placement, you have a group of machines, and each of them store their checkpoint on their own machine and the other machine. But there is another way, which is the ring approach. In the ring approach, you have a logical way of storing the machine. Imagining the machines, and you store each replica on itself and on the next machine. And the paper mentions that if you have 4 machines and you want to store 2 checkpoints and they're dividable, you can use grouping approach. But if that's not the case, you will use the mixed approach, which is a mixed way of using the grouping approach and the ring approach. The second challenge is handling training inference. They mentioned that there are lots of times that the model is idle. So in synchronous training, you have to wait for the other model. So in that time, you're not communicating your training information with the memory. So you can utilize that to do your checkpointing. So as you can see in this picture, you are kind of interleaving training communication and checkpointing communication so that they are not done at the same time. And also, the paper gets into more detail of how to actually do this. So the naive way would be to just store the whole checkpoint in GPU memory and then send it to the other GPU. So GPUs are also connected with each other. So you can communicate directly from GPU to GPU. I mean, they have fast interconnects that give lots of bandwidth, but they mentioned this is not a very good approach because you run out of memory, because these checkpoints are huge most of the time and you have limited GPU memory. Another way, which is mentioned in C, is that you just split it and then communicate it to the other GPU and then move it to the CPU. But the main problem with this is that when you copy GPU memory to CPU memory, you have to block and you cannot receive any other information. The final way that they use is pipelining. So what you do is that you send information, checkpoint information from GPU to GPU. But at the same time, in a pipeline way, you're also copying it to the CPU so that you don't block the communication. And for the experiments, they have a bunch of experiments about their training efficiency. And so what is interesting to me here is this figure 9 here, which means the probability that they can recover from checkpoints. But what I would like to see is how long does it take? I would like to see what is the cache hit rate. I don't know how that translates here, but I think that's the same idea. And also this is the iteration time for training 3 large models using Gemini with checkpointing and with no checkpointing. And for checkpoint time and frequency, what was interesting to me was this one, which shows that their approach is effective because they can have much more frequency, so they can checkpoint much more per hour compared to the Strawman approach and also a previous solution called HiFrec. And also the checkpoint time has been reduced because now you don't have to go to the persistent storage every time. So, and also with the available bandwidth, so you get much more bandwidth because you can just put it on the memory which has higher bandwidth. And yeah, so that's all for Geminis. And yeah, I would be happy to talk about the paper.